Welcome to Confidence Intervals, Part 2, Module 6, Lesson 3. This is a really big lesson. Let me begin by discussing confidence intervals for variance. We can recall from Lesson 2. Say you have a random sample, x1 through xn, from a normal distribution, mean mu, standard deviation, sigma. Then this random variable, n minus 1 s squared over sigma squared, here s squared is the sample variance. Well, it is a chi-square random variable with n minus 1 degrees of freedom. Okay, now what I have graphed here, this is the probability density function for chi-square with 9 degrees of freedom. And the way I have it, let's see, this blue, we can think of this as having area 1 minus alpha. My alpha in this picture is 0.1, and then these are area alpha over 2. I will shade these in green. Now, the thing to observe is we do not have the symmetry for this distribution that we have with the normal distribution or the t-distribution. And so unlike when we were doing confidence intervals for population means, when we had a random sample from the normal distribution, when we make confidence intervals for population variance, this will not be centered around our point estimator of the variance. And our point estimator is the sample variance. Okay, we will, however, use this chi-square sub alpha over 2 and minus 1 degrees of freedom. This is the alpha over 2 quantile. And chi-squared sub 1 minus alpha over 2 with n minus 1 degrees of freedom. This is the 1 minus alpha over 2 quantile. What we want here is this. So this n minus 1 s squared over sigma squared to be strictly less than this 1 minus alpha over 2 quantile and strictly bigger than this alpha over 2 quantile. Now, we are trying to construct a confidence interval for sigma squared, and so we need to do a little bit of algebra here. S squared comes from my sample. Okay, the first thing I can do is I can divide everything by n minus 1 times s squared. N minus 1 is positive, s squared is positive, and so dividing by n minus 1 times s squared will not change the direction of my inequality. All right. Well, remember, I'm trying to get a confidence interval for sigma squared. And what I have is 1 over sigma squared. So I can just take 1 over, 1 over, and 1 over. Okay. On the inside, I'll have sigma squared. Now, let me do some magic with my iPad. All right. What is left is my inequalities change directions. So this will become greater and greater. We can think this way. I'll erase this in a moment, but say we know 1 over 5 is less than 1 over 3, say. And so when we take 1 over that, it will go the other way, like this. So this is basically what I have used here. It just looks complicated with so many indices. Very nice. Well, now we have it. Here is the upper bound of this confidence interval, and here is the lower bound of this confidence interval. So let me just write that. Fantastic. Now, this is exactly what we just wrote. I have it nicely typed here. This was our 100 times 1 minus alpha % confidence interval for the population variance. And similarly, we can construct these one-sided 100 times 1 minus alpha % confidence intervals for the population variance. Well, let's suppose I want a confidence interval for the population standard deviation. Okay, we know standard deviation is the square root of the variance. And so maybe I will come back here, copy this, and paste, except for my lower limit and upper limit, I need to take the square root of what I'm looking at right now. Wonderful. And I have also filled in the one-sided 100 times 1 minus alpha % confidence intervals for the population standard deviation. Here's an example. Suppose we have a random sample of size 16 from a normal distribution, mean mu, standard deviation sigma. We are given the sample standard deviation is 2.2. We'd like a 95% confidence interval for the population variance, 95% confidence interval for the standard deviation, population in this case too, and then a one-sided 95% confidence interval for the population standard deviation. Now I have just included these. We are only asked for one-sided, so we will do this one, but I have included these from the last 2 pages, our formulas. Okay, n minus 1 is 15, so let's write some things here. Number 1, our confidence interval will be 15 times 2.2 squared. That's going to be in the numerator of both of these. Then I have 2 different quantiles in the denominator. Here, alpha over 2 is 0.025. So here, this will be chi square 0.975 with 15 degrees of freedom, and chi square 0.025 with 15 degrees of freedom. Now, let's go to R and calculate some of this. Well, if I'm just interested in these 2 quantiles that I see in the denominator of my lower bound and upper bound, I can calculate this in R. I use Q, this chi-seq. Make sure you use 15 degrees of freedom. This is the 0.025 and 0.975 quantiles. However, exactly what I have calculated here, I could also do as a line in R. Maybe I will take an initial step and write the quantile down. So we have about 27.5, and then this 0.025 quantile, we have about 6.3. The interval, we get 2.64 to 11.59. This is number 1. Next one, we just copy and paste, but we are wanting standard deviation. And so we just take the square root of everything we see. So we will have square root of 15, square root of 15, here, and here. For this, if you want, you can use a calculator, but we can also use R. So in R, I have used this line that you see right here. We have 1.63 to 3.40. At this point, I'm going to erase our guidance and move some things around so we can work on number 3. For number 3, we want a one-sided 95% confidence interval. So square root of n minus 1 is still the square root of 15. This is for the standard deviation. And then I have the sample standard deviation. We will have a different quantile here. We want 1 minus 0.05, which is 0.95, still with 15 degrees of freedom, and then to infinity. Now, if all we want is the Quantile, here it is. It's 25.0. So I will put that as an intermediate step. And finally, we see this lower bound here. It is 1.70. We have 1.70 to infinity. And there are some lines separating my work. What a wonderful example. Now, let's talk about confidence intervals for population means again. So until now, in part 1 of confidence intervals, and also our discussion of confidence intervals for population variance, everything we have assumed that the data is a random sample from a normal distribution, mean mu, standard deviation sigma. Well, the question is, what if we do not have this assumption? So when we're dealing with population means, it's wonderful. If you recall, when we discussed sampling distributions, these approximately hold as long as n is very large. As a rule of thumb, the approximation is good when you have at least n equals 30. So the answer, we can use z intervals, which comes from here, and t intervals, which comes from here, on all data sets when n is large. So now let's talk about what if we had a random sample from the Poisson distribution. So the Poisson distribution is not normal. But what's our point estimator here? This would be true for either maximum likelihood estimation or method of moments. If you want to estimate this parameter lambda, we use the sample mean. Okay, now, since the Poisson variance is also lambda, you can use the square root of the sample mean to estimate the population standard deviation. So as long as n is large, we can use a z interval with estimated standard error. Well, generally, this is what we want. And when we don't have that, we use this. But when we are working with a Poisson random sample, we can use the square root of x bar. That would be our estimate of the population standard deviation, and then divided by the square root of n. So we will use this in our z intervals. And let's do an example now. We have 50 observations from a Poisson distribution, random sample, and the sample mean is 8.42. We want a 90% and 92% confidence interval for the parameter lambda. Now, what I have done is just written out explicitly what this z interval is. So this first one is for 90%. We would have 0.5 and 0.5 in each tail. You could either write it like this, or we could write x bar plus z sub 0.05. This would be another way to write it because of the symmetry of the standard normal distribution. Well, for this example, this estimated standard error would be the square root of 8.42 divided by n, which is 50. So we will use that really in both confidence intervals. Now, let us go back to R to calculate these. We can define variable x bar, variable n, and then here's our first confidence interval. This is the 90% confidence interval. We can write it down. We have 7.75 to 9.09. This one is the 90% confidence interval. All right, the next confidence interval, we are just changing the quantiles we use. So you see here I use 0.4 and 0.96 quantiles. We can also write this one down. This one goes 7.70 to 9.14. This was our 92% confidence interval. The final thing I want to mention is about confidence intervals for binomial proportions. So let me set this up and we can talk about this some. Suppose we have a Bernoulli random variable x with success probability p. What does this mean? Well, this random variable is 1 with probability p and 0 with probability 1 minus p. And so the probability mass function is given right here. Well, as a remark, we can without a doubt calculate expected value and variance by hand. These are short calculations. Okay, it's a very nice review, in fact, of stuff from earlier modules. So the expected value of x, we take x times f of x plus the next x value times f of x. And I have added over these two values in the support. Well, we just get p. The variance, we take expected value of x squared minus, well, we could do it this way, expected value of x, quantity squared. So this was our shortcut for variance, but perfectly fine. Expected value of x squared, we take 1 squared times f of x plus 0 squared times, okay, f of x. And then subtract off p squared. We get p minus p squared, or p times 1 minus p. Wonderful. Now, suppose we have a random sample. And what I mean by this is x1, x2, out through xn are independent and identically distributed Bernoulli random variables. Let capital Y be the sum, x1 through xn. Okay, capital Y. Well, just think about this for a moment. It gives us the number of successes in these n Bernoulli trials. Have we talked about this before? Absolutely, we have. Capital Y is a binomial random variable. So we have success with probability p, failure with probability 1 minus p, and then capital Y is the number of successes out of these n trials. Well, we know from either properties of sums, and here x1 through xn are independent, or just thinking about the binomial random variable, the expected value of y is np, and the variance of y is np 1 minus p. Okay, well, here's the beautiful thing. For a large n, the central limit theorem applies. If you recall, central limit theorem was a statement about sums of n independent, identically distributed random variables. And so y would be approximately normal, mean mu, standard deviation sigma, where the expected value, this mu, is n times p, and sigma is np 1 minus p. Oh, not negative, just like this. Okay, so this was actually a really nice review of stuff we've learned this semester. But the question is, where's the confidence intervals and where is even the point estimator that I'm interested in here? So we're interested in estimating the probability of success, P. And the best estimate that we have, either thinking about sampling from this Bernoulli random variable n times, or taking one observation from the binomial distribution with parameter n, and then this success probability that we don't know, p, well, point estimator p hat, it's this capital Y over n. Well, this is fantastic. We have a way to estimate the success probability P. But in this module and in this lesson, we are interested in an interval estimation. So how do we do this? Well, for large N, we can use Z intervals. The margin of error will be this quantile, which comes from the standard normal distribution, times this estimated standard error of the point estimator, p hat. Okay, so first of all, what is the variance of p hat? The variance of y divided by n squared. The variance of y is n p 1 minus p, and then over n squared. This is p 1 minus p over n. Well, what we would like here is the square root of this. That would give the standard deviation. However, we don't know what p is. We're trying to estimate it. So what would be the best estimated standard error of p hat? Okay, just take a square root. And instead of p, we use our point estimator p hat here. So if we look below, I have the formula for the confidence interval already there. Here's this point estimator, and then this part is our margin of error. We have the quantile coming from the standard normal distribution. We have the estimated standard error of the point estimator. Maybe my note, because sometimes this is how we will type it into R, because of the symmetry of the standard normal distribution, this minus z sub 1 minus alpha over 2 is just this here. Sometimes you will see me use this in my R commands for simplicity. Now, my final remark in this lecture video is just this. Z confidence intervals tend to work well when NP and N times 1 minus P are both greater than or equal to 10. And this is just a rule of thumb here, but it is worth mentioning. All right. Well, thank you so much, class, and I hope you have enjoyed this second part to our confidence intervals. Thank you.